Now we will look at how we can vary this potentiometer in order to set the voltage at this node to be equal to minus of 0.273 volts. And if we can remember from this particular portion of the circuit, voltage at this node was equal to negative of 2.5 volts, which is the same as the voltage at the other end. And so if we zoom into this part of the circuit and we break down this potentiometer into two parts, then we can say that voltage at this node is Vx, same as here. Voltage at this node is minus of 0.273 volts, same as this point. And then we have broken it into two parts. This 1 kilo ohm potentiometer, one of it being x kilo ohm, other one being 1 minus of x kilo ohm. And then applying KCL at this node, we can write I1 plus I2 is equal to I3. Now we can frame the node equation as I1 being equal to Vx minus of minus 0.273 divided by 1 kilo ohm. I2 is equal to minus of 2.5 minus of minus 0.273 by 1 minus x kilo ohm, and I3 is equal to minus of 0.273 minus 0 divided by x kilo ohm. So from here, from this expression, we can frame a quadratic equation like so. And then we can take one example to identify the value of x. So let's say that we had derived the expression for Vx as 0.00091 times TA volts, and assume that the ambient temperature was 25 degrees centigrade. So we are working in the lab condition at 25 degrees centigrade, where the temperature of the cold junction is this much. So we have Vx is equal to this number, and substituting Vx in this equation, we arrive at this quadratic equation, upon which if we solve it for x, we obtain two values. So both the values will be real, but one of them is negative and must be discarded, and we retain the positive number, and this is equal to 0.1219 kilo ohms. So this means that if we set x as 122 ohms, so referring back to this circuit, if we set x as 122 ohms, then voltage at this node will be equal to minus of 0.273 volts.